All right, we are going to do chapters 10, 11, and 12 all together, as mentioned, because chapter 10 is gases, chapter 11 is liquids, and then obviously chapter 12 is solids. We're going to just bundle them all together in one shot. And we are here for chapter 11, section 11.1, and we're going to focus on liquids. And when we talk about liquids, we're going to talk about the three types of forces or intermolecular forces that can exist in liquids. Now when we just got done talking about gases. What's the key difference between solids, liquids, and gases? From a chemistry standpoint, it's the distance between particles. Remember that solids are very close to one another, liquids are kind of in between, and gases are really far apart. So kind of an idea, just remembering that. Now, just a simple vocabulary term here. Because liquids and solids are closer together, we refer to them as their condensed phases. All right, so just if you hear the word condensed phases, we're talking about a liquid or a solid. Now, we reviewed this for gases in chapter 10, but here's just kind of some comparisons between solids, liquids, and gases. Most of them you know. For example, liquid assumes the shape of its container, does not expand to fill its container, is virtually incompressible, and flows. Right? Those are common characteristics of liquids. Solids, it has its own shape and volume, does not expand to fill its container, is not compressible, does not flow, and diffuses with solids extremely slowly. So just kind of some ideas about matter. And then we talked about gases already in chapter 10 about some characteristics of gases. If you want to take a picture of that, go ahead and knock yourself out, but it'll be good. So intermolecular forces. Today, this section 11.1 is really focused around intermolecular forces. And what are intermolecular forces? They're attractions between two molecules. Now, one thing to keep in mind is that intramolecular forces, or forces within the molecule, are much stronger than intermolecular forces, forces between the molecules. But we're going to talk about really the three major types of intermolecular forces and how those affect the physical properties of compounds. Now, these intermolecular forces are grouped together and they're referred to as van der Waals forces. Now, we talked about the van der Waals equation earlier in chapter 10. Same type of deal, except now we're dealing with liquids and van der Waals forces. There are three types of van der Waals forces: dipole-dipole interaction, hydrogen bonding, and London dispersion forces. And we're going to talk about what molecules are more prone to each one of those three types of forces. So we are first going to start with London dispersion forces, and we're going to kind of tell a story. So if we look at a helium atom as our example, the helium atom has 2 electrons. Now, one would say that the electrons are always going to be at the opposite sides of the atom because they repel one another, correct? As you can see here in atom A, and as you can see here in atom B. They're typically on opposite sides of the atom. Right? So no polarization would happen. Typically that's what happens. However, occasionally it's possible that they happen to end up on the same side of the atom. So here in atom A, right, they're on opposite sides, but occasionally they can occur to appear on the same side of the atom. What that generates is that generates an instantaneous pole on the atom, where we have a negative rather than the charge spread equally throughout. We're going to have the negative charge focus on the side of the atom where the electrons are, and a small positive charge focus on the side of the atom where the electrons are not. Now what this will do is another helium atom nearby, then we'll have what we call an induced dipole, where because electrons are always repelling one another, those electrons will be forced to one side of the atom because it's going to attract a positive and negative. So in atom A, we have a random dipole happen because the electrons randomly move to one side of the atom. In atom B, we have what we call an induced dipole because the electrons are attracted to that positive charge from atom A. So this is a London dispersion force. Now, London dispersion forces happen between what we call an instantaneous dipole and an induced dipole. Now, what's the difference? An instantaneous dipole is something that happened in atom A, where the atoms randomly, or where the electrons in the atom randomly were on one side by coincidence. An induced dipole is where a second atom is attracted to atom A, changing where the electrons are in that atom. These forces are present in all molecules, whether they are polar or nonpolar, and the tendencies for an electron cloud to be distorted, like they were in our example between atom A and atom B, is called polarizability. 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 All right? So that's London dispersion forces. Now, what are some things that affect London dispersion forces? Here's the big thing. Shape of the molecule affects London dispersion forces. Long, skinny molecules have stronger forces than short, fat ones. So we're going to go shape. If we're going to summarize here, we're going to go shape, and shape is kind of the first idea, all right, that kind of can affect that. So shape slash what we call surface area. Long and skinny trumps short and fat. What other factors can affect London dispersion forces? Molecular weight. Larger atoms have large electron clouds that are easier to polarize. So we talk about shape and weight. All right. Shape and weight are going to affect London dispersion forces. So you can kind of see, all right, kind of how it works here. So that was London dispersion forces, kind of how you can have an induced dipole and an instantaneous dipole. Now we have things called dipole-dipole interactions, which is just a random, all right, permanent dipole on an atom. Now, permanent dipoles happen on atoms all the time. For example, water is a very polar molecule. It's going to have a dipole where one part of the atom is positive and one part of the atom is positive and one part of the atom is negative. Now, when this happens, it's going to attract like molecules. Well, how is it going to attract like molecules? Because the positive end is going to be attracted to the negative end. The more polar the molecule, the higher its boiling point. Now, which one's going to have a greater effect? Dipole-dipole or dispersion forces, since they are both focused around dipoles. If two molecules of comparable size and shape, so if they have comparable size and comparable shape, dipole-dipole interactions will be the dominating force. However, if one molecule is much larger than the other, dispersion forces will likely determine its physical properties. So keep that in mind. If the molecules are comparable in size and shape, it's going to be a dipole-dipole interaction. If one molecule is much larger than the other, it's most likely going to be a London dispersion force affecting it. So we can kind of go on and explain that, but you kind of have the general trend there. The third type of force in which I want to talk about today is hydrogen bonding. Well, how does hydrogen bonding occur? It's with hydrogen atoms. But the key to this is it's hydrogen atoms, but it's hydrogen atoms typically only bonded to nitrogen, oxygen, and fluorine. So nitrogen, oxygen, and fluorine. Why those three? Because those three are unusually strong dipole-dipole moments with hydrogen. So we call this hydrogen-hydrogen bonding. And what happens here is you can see that if in this example up top here we have two water molecules. The H in one of the waters is attracted to the oxygen of another water molecule. And I could draw a third water molecule, and the same type of attraction could happen with the third water molecule. And these are responsible for some physical properties that you see in liquids. So we have London dispersion forces, dipole-dipole, and hydrogen bonding. Now hydrogen bonding arises because of the high electronegativity difference between hydrogen and nitrogen, oxygen, and fluorine. So that's hydrogen bonding. They call a fourth one ion dipole. I'm not going to consider that. And if you have to summarize intermolecular forces, you kind of got to figure out what the intermolecular force at play is and how it's going to increase in its strength. Here's kind of a flow chart to kind of help you out here. What you have, though, is increasing interaction strength. So the increasing interaction strength, you're going to have higher melting points and boiling points on this side and lower melting points on this side. And the chart here kind of shows which one trumps. You have London dispersion forces only. So we have London first, followed by our dipole-dipole, followed by our hydrogen bonding. All right, I talked about ion dipole forces. Not going to worry about that one as much. And then we have our ionic bonds over here, which we know ionic bonds have our highest melting points in general anyway. So which force is the strongest? London is the weakest, followed by dipole-dipole, followed by hydrogen. So hydrogen bonding is the strongest, dipole's in the middle, and London is the weakest. So those are the really three types of intermolecular forces we're going to focus on when we talk about liquids, and this is the end of section 11.1.